In this video, I'm going to give you a rough explanation as to why, when you convert it from Cartesian coordinates into spherical coordinates, we would need to stick this weird thing in here. And I do mean a rough explanation, because for you to fully understand this, you need to go beyond Calculus 3. So remember, we've already done this in one of the earlier videos. With spherical coordinates, you would specify the radius of the sphere, which is given by rho. You would specify the angle it makes with the z-axis, which is given by phi, and this angle here, you can swivel this back and forth here. The angle here is theta. With those three arguments, you can specify any given point in 3D space. We've already seen this in the previous video. So now for the explanation. Our motivation is to try and find the relationship between the volume as you nudge the radius, as you change the radius. So as you change the radius, so this is the radius of the sphere. As you change the radius, which is given by delta rho. So you've got to imagine this point here. You nudge the radius slightly, and then you nudge the angle. You nudge this angle slightly. When you nudge this angle slightly, it will move like this. It will move like this. So this is your delta phi. So as you nudge this angle slightly, this point here will swivel back and forth like this. It will swivel back and forth like this. And then what happens as you nudge the angle theta? So this is your angle theta here. As you nudge the angle back and forth, your point here, your point here will swivel back and forth like this. It will swivel back and forth like this. So this angle here is really delta theta. So that's this bit here. So when you change the radius slightly, that represents this thing here. That's your delta rho. When you swivel this back and forth, it represents the change in the angle here. And then when you swivel this in this direction, it represents this thing here. Well, what is the how does this volume here relate to the three change in these arguments? So as you change these three arguments, how will that affect the volume? As it turns out, it will have this kind of a relationship, but we need to understand why. Okay, so hang on. Before we start, I need to take you back to high school maths. Given a circle, let's say it has an angle of 23 degrees, the radius is 7. What is this arc length here? So back in high school, it would be 2 pi r divided, you cut up into 360 equal pieces, and then you get 23 pieces. But in radians, it would be, so let's say in radians, it would be, let's say you've got a circle radius r and an angle theta. In radians, it would be 2 pi r divided by 2 pi, and then you times by the angle theta. And then, so the arc length is really given by r theta. So this is back in high school. So the point here is that given a circle, if you want to know the arc length, it's just simply the radius times the angle. Okay, and from one of the earlier videos, given the radius of the sphere as being rho, we know this length here. This length here is given by this, and I've already given you an explanation. So just remember that this length here is given by this. So if you want to know this arc length here, as you swivel it, if you want to know this arc length, you just get this times by delta theta in this case, because you've got the radius, and then you just times it by the change in the angle. And then if you want to know, as you swivel this vertical angle, it would be this. And then if you want to know this arc length, it would be this length, which is rho, the radius of the sphere. the radius of the sphere, and then you times by the change in the angle, which is delta phi. So going back to here, hang on, going back to here, this length here is given by delta rho, because it's just a straight length. So this length here is delta rho. It's a change in the radius of the sphere. If you want to know this length here, it would be the remember, as you swivel this angle here, it will represent, so this length here represents this thing here. So if you want to know this length, it would be the radius of the sphere, which is rho, and then you times by the change in this angle here. It would be the change in this angle here. So this length here, you can imagine it as being rho delta phi. So that's this length here, and then this thing here, this. So as you swivel theta, this length here, this arc length here, because this is part of a circle here, well, this arc length here represents this thing here. So so that would be this radius here, which would be hang on, which would be this length here is given by this. So if you want to know this arc length, it would be this radius, which is this one here, times by the change in theta. So this arc length here is given by this. So going back down here, so it's so this length here is given by rho sine phi, and then you times by the change in the angle theta. So so roughly the volume of this thing here would be the height times the base and then times this depth. So it would be this times this, which is this length here, and then times with this thing here. So the change in the volume is given by delta rho times rho times this length here, which is rho delta phi, times this thing here, which is rho sine phi delta theta, and then so this rho times rho here, that would give you rho squared, which is this thing here, rho squared, and then see this sine phi here, that's your sine phi here, and then you've got your delta and delta, that's this delta. So I hope you can roughly accept that as you nudge these three arguments, it will have this kind of an effect on the volume here. I know it's not a perfect cube, but as you take the limit, as those deltas tends to 0, you can imagine it as becoming a cube. And remember, this is just a rough explanation to give you the relationship between this and this. But for you to fully understand it, you need to study beyond Calculus 3. Okay, so at the moment, for the time being, it gives you, I hope you can roughly accept that when you convert it from Cartesian coordinates into spherical coordinates, you would need to stick this weird thing in here. Okay.